Hello everybody, this is John Buck back with another array signal processing video. This video is the third one in this series discussing array gain. That is, how does an array help us improve our SNR against uncorrelated background noise. So this assumes you've already watched the first two. If you haven't, you should just pause this video and go back and review those. And to finish that discussion, the question we'll answer in this video is, how do I choose a beamformer to maximize the white noise gain? Right? In the first two videos we went through talking about how combining the array of the sensor array data can help us improve the SNR, and that when the background noise is uncorrelated from sensor to sensor, what we call spatially white noise, we find that the formula for white noise gain is 1 over the norm of W squared, right? 1 over the magnitude of the weight vector squared. And so a natural question is, well, what set of W should I choose to get the most noise gain possible? In this video, we'll do that two different ways. The first way, we'll just straightforward plug and chug with algebra, with a little wrinkle of what we have to do for maximizing functions of complex variables. And then I'll finish with a quick smart and lazy approach exploiting Cauchy Schwartz inequality to show how it's very straightforward to find what the maximum array gain is. And sort of like a good murder mystery, we'll find out the suspect was right in front of us all along, at the risk of giving a spoiler. Okay, so let's switch over to the whiteboard and start on that. Okay, so again, our goal now in this, we're saying, how do we maximize white noise gain? Remember, we saw for the case when the covariance, when the noise covariance is uncorrelated from sensor to sensor, then the array gain is 1 over the norm of W squared. Where we use the abbreviation AG sometimes for array gain. And for the special case, we sometimes just call this white noise gain or abbreviate it WNG. And this 1 over the norm of the weight vector is very important in arrays, even when the noise isn't white, because we'll see in a few weeks it tells us something about the sensitivity of the array to errors in the position or gains of the elements. But I don't want to get too far ahead of myself. But it is I do want to emphasize this is very important. So the natural question is, well, if I want to maximize this array gain, it seems I want to just make W as small as possible, right? And so you say, well, I'll just keep making W smaller, and I'll just get more and more array gain. So if I make the norm of the vector smaller and smaller, pause for the video for a second and think what's wrong about that or what's incomplete about that argument. Why can't I just make infinite array gain by setting W equal to 0? Okay, assuming you've paused and thought about it, I can't set W equal to 0 because then I would basically be turning the array off, right? I have an additional constraint we haven't met here. Not only do I want to maximize array gain, but in general, I still have some desired gain for the main lobe in the look direction, right? We usually, just to pick a choice, we usually call it unity gain, right? So we need to assume that the inner product of W with the desired replica vector in the desired direction will be 1, right? So that we have this, so this is a constrained optimization, not an unconstrained one. If I set W equal to 0, obviously the left-hand side there is 0, and I can't make the constraint. And again, the idea of VT is the replica vector in the desired look direction. So if we want to find an extreme value, either a minimum or a maximum, with regard to a constraint, our friend here is, again, pause and think about it for a minute, Lagrange multipliers, right? Although it's a little different because W, the thing we're optimizing here, is a complex thing. Also, to keep the math simpler, we're going to look at this and say, well, if I were going to try to minimize, or sorry, if I want to maximize the array gain, that's the same as minimizing this denominator subject to the same constraint. So I'm going to do it that way, and I'll set up the equation the Lagrange multiplier that way instead. Okay, so we're going to set it up this way where we're minimizing this, remembering W Hermitian W here is the same as norm of W squared, right? But we're writing it this way because we want to make explicit the dependence on W Hermitian and W for reasons I'll mention in a minute. And if you choose the face center of your array and your symmetry so that everything is real, like the beam patterns are real, this will be okay. But to actually, as Van Trees points out, we have to be a little more careful. If we don't know for sure lambda is real and the W Hermitian V will be real, we need to take that into account and use the real part since we know our objective function here is real. So we're actually going to revise this a little bit for the more general case. Right, so we're going to say I've got this inner product, and then one of those annoying professor things, I'm going to write this as 2 times the real part of the constraint for sneaky reasons because I have an ulterior motive knowing where I'm going next, which is I'm going to now write this in terms of the conjugate, the sum of the conjugates of the constraint. So I can now rewrite this as the term inside the brackets plus its conjugate, would give me 2 times the real part. Okay, so these are equivalent just because I've taken the conjugate of everything inside here. And now we say, well, normally if I want to find an extreme value, either a maximum or a minimum of a vector function, pause for a minute and try to refresh your memory about what we do. Right, we take a gradient with respect to w and set it equal to 0. So let's make a little more space here. And that worked fine for real vectors, but when we're working with objective functions like j that are a function of complex vectors, we need to worry about this issue from complex analysis called analytic functions. We need to make sure that we're taking the derivative in a way that for the well-behaved functions, things stay analytic. I'm not going to get into a long discussion of this. I'm sure you can find videos of analytic functions. And there are a couple ways that people approach this for taking the gradient with respect to a complex vector. The one I'm going to recommend is the same one that's in the Van Trees book that all tracks back to a Brandwood 1983 paper from the Proceedings of the IEEE that I will put the reference for that in the description box for this video if you want to track it down. If you're going to do a lot of work on proving certain arrays are optimal, you might want to understand that. But otherwise, the short version is this, is we pretend that W Hermitian and W are independent vectors. We don't pretend that they're the same numbers that are just conjugates. We pretend they're completely different vectors. So when I take a gradient with respect to W, W Hermitian is like a constant and vice versa. And we can do it either way and set it equal to 0 and treat the other one as a constant, and we'll get to the right answer for reasons the Brandwood paper explains and Van Trees talks about some when he talks about gradients with complex things. But let me summarize that. And for most of the problems in this class, in the book, I should clean that up. That should be clearly W Hermitian. It's usually a little easier to take option 2 because then it leaves the W's alone, as we'll see. And so Van Trees usually does that, but either one will work. You just might need to do one more conjugate at the end to get your answer in terms of W. Okay, so let's roll this up and apply option 2. We'll stick with this one. This is my favorite for most problems. I usually start here and then decide to switch if for some reason it isn't working for me. So let's apply that to my equation from up at the top. Let me copy that down. Right, so now when we take the gradient, the first term, if I take the gradient with respect to W Hermitian of this first term, this goes away and I'm left with just the W. For the second term, I'm left with, well, the minus 1 term goes, the gradient is 0, and I'm left with a plus lambda Vt. And the third term, when I'm taking the gradient with respect to W Hermitian, this W is like a constant, so this whole thing is an independent thing. The whole gradient of this last term goes to 0. And then I set the whole thing equal to 0, giving me W is equal to, for my optimization, it tells me my array weight vector should be minus lambda Vt. And even though we haven't solved for lambda yet, we're already seeing something really important, which tells me that the weight vector should be a scaled version of the replica vector we're looking for. So we already kind of know the answer to this if we think of it that way, but we can follow it through the classic Lagrange approach now, is plug this W in to the constraint, right? Plug it back in up, and then solve for my value of lambda that satisfies the constraint, right? So if I do that, I get a W Hermitian becomes, I'm going to assume, sort of knowing the answer, that lambda is real. So that W Hermitian becomes minus lambda V transpose Hermitian, right? That's this W Hermitian term, times another V transpose equals 1, right? That's the equivalent of saying V Hermitian V transpose must equal 1. Right, so if I do that, now I can say, well, this term here, V Hermitian V, for the way we write replica vectors, is n, the number of sensors, right? This is norm of V squared. And so solving for that, I get that lambda is minus 1 by n. And so my weight vector is 1 over n times V transpose. So pause for a minute. Does that look familiar? It should, right? This is saying that if I want to optimize the white noise gain, my weight vector should be, this is the conventional delay in some beamformer, that I choose my weight vector just to be the replica vector of the steering direction I'm interested in, where I want to direct my beam, or the look direction, scaled by 1 over the number of sensors to make sure that I have unity gain. Right, so we're back in the delightful position of having set off in a new direction to discover a brand new beamformer and pursued this algebraic process to maximize our array gain, only to learn that it was our old friend, the conventional beamformer or delay in some beamformer all along that provides the best white noise gain. Okay, so, and in fact, there's a geometric region that's quite straightforward to see, actually. If we think about it, let me switch to another sketch here. Right, if I think in sort of an abstract space, right, the weight vector is itself a vector. This is an n-dimensional complex space. I can only kind of draw 3, but work with me on this, right? So here's our look direction, VT. And what we're saying is if I think of the set of all possible weight vectors that have the unity gain constraint, that's defined by an infinite plane. I've just drawn a segment of it here. But the infinite plane that is intersects as normal to this vector, right, is defined by the normal being the plane that's defined by VT as its normal vector, intersecting at the point 1 here, right? And so all the points in this red plane would be that. And if I think of them, I could say, well, I can write each of those points. Any W in this plane, like I've shown here, can be decomposed into the sum of 2 vectors. The part that's parallel to VT and the part that is perpendicular to it, right? So if I choose, you know, by definition, if I now think of the unity gain constraint with this vector, I can plug in like this. And again, being clear that little thing, this is a parallel sign, not an 11. Sometimes this is parallel and perpendicular. And now I distribute this through. We can simplify this because by definition, this second term is 0, right? This is a vector that's defined to be perpendicular to VT, so its inner product must be 0. Right, so I'm only left with this here, and again we know then to make this be the unity gain, this will be 1 over n times VT for the W Hermitian dissatisfied. So we know every vector in here has the same W parallel, right? It must have W parallel is going to be 1 over n times VT. So every vector in this plane has the same part that's parallel to VT, which is right along this axis. And then all the elements in the plane are just adding different W perpendiculars here to form to get all the different vectors in the plane. But if I think about, well, my goal in optimizing white noise gain is I want to minimize, find the point in that plane that minimizes norm of W squared, because if I minimize that, I'll maximize the white noise gain. And say, so out of all the points in the plane, how do I minimize this? Well, because the 2 vectors are perpendicular, the norm of the whole vector squared is the sum of the individual orthogonal components. Or rather, it's the sum of the norm of the orthogonal components. When I have an orthogonal decomposition of vectors, the norm is the sum of the norms of those orthogonal components. And we know this first one is the norm squared is always going to be the same, right? It's going to be 1 over n. Whereas meanwhile, you know, the W perpendicular is going to be whatever it is carried down until I'm left with that the norm of W squared must be 1 over n plus whatever I get from the perpendicular component, right? So that the norm of any weight vector in this plane that has unity gain, of all the possible ones with unity gain, will be 1 over n from the parallel component plus whatever it gets from the perpendicular component. They should be W perp, not W perpendicular, not W. But that last term can only, right, because it's a norm, it must be greater than or equal to 0. Right, so this term here is greater than or equal to 0 because it's the norm squared of a vector. So that tells me overall that the norm of any vector must be greater than or equal to 1 over n. And it will only equal n when this term is 0, which means that W just is the parallel component, which is the answer I had up here. Right, so this is if I set, I don't know why I've been writing in red all along. I don't feel that angry. So if I set W equal to the parallel component right? So this is the sort of geometric argument for why we get the same answer as Lagrange. Another way I've heard this described is to think of all the vectors, all the weight vectors of a given magnitude or a sphere or a ball at the origin, right? You could imagine a circle working its way out, right? So all the vectors of a given norm squared A are a sphere centered at the origin with radius A. Well, I guess radius A square root of A. And we're going to just keep increasing that ball until it touches the first point in this plane up here, right? We're saying these are all the ones of a given norm, and I'm just going to keep increasing the norm until I find the first one that also satisfies the unity gain constraint. And you can sort of visualize in your head how that will just touch here when it's just tangent to the plane. The sphere gets big enough to just touch the plane and has the norm given by the conventional beamformer. So those are two ways. I know I've gone a long time, but rather than make another short video, those are the main ideas so the conventional beamformer maximizes the white noise gain, or equivalently, you can think of this as, we sometimes say, it's the spatial matched filter. We learn in sort of fundamentals of detection theory that the best way to detect whether a signal is present in white noise or to maximize the SNR for a signal is to correlate with the thing you're looking for. If you know what you're looking for in the data in your hypothesis test, doing a correlation, which is like doing a convolution with the flipped thing, maximizes the white noise gain, and that's a very standard detection strategy. So by setting the weight vector to be collinear, essentially a scaled version of what we're looking for, we're making a matched filter in space across all the sensors. So you can stop here if you want. I'm going to go a little bit further and show the Cauchy Schwartz thing, because it's probably not worth, it's just a few minutes, I think. It's not worth a whole new video. But that's the main takeaways for today. So if you're still with me, this is sort of like the little thing I mixed into after the trailers when you go to the movie. A quick little highlight of a Cauchy Schwartz proof of maximizing the white noise gain. I've become a huge fan of Cauchy Schwartz proofs since I read the Cauchy Schwartz Masterclass. Great book. I'll also flag that in the description, maybe with the link, if you're curious to see really smart ways to prove a lot of inequalities in math when you can find them with a geometric interpretation. The way it works here for array gain is if we sort of go back to our formula from the earlier videos of the array gain and stop before we put in the unity gain constraint action. Now at one point we had this, the array gain is the SNR out over the SNR in, and if we have spatially white noise, that is the noise covariance that was in the denominator was sigma n squared times I, we had an expression that looked like this, right? That is the weight vector times the look replica magnitude squared over the norm of W squared. And here's where Cauchy Schwartz comes in. Remember, for those that don't remember it from linear algebra or sort of Calc 2 or 3, wherever you learn vectors, the inner product is always, the inner product squared, magnitude of the inner product squared, is always less than or equal to the norm of each vector, right? So it looks like that, where again, this little bracket notation is sort of physics for inner product. When the vectors are real, it becomes a dot product. Right? And so we get something like this. Now, when we're working with complex vectors, that inner product, importantly, as we've seen already for like a beamformer, and I add this in red because it's so important, right? That one of the terms is conjugated for complex vectors. And so that's what we have here. But this is the main idea. And even more importantly than this inequality is that the equality exists if and only if A and B are scalar multiples of each other, which is to say, we say collinear is the fancy word for that. Right, so A is some scaled version of B, where lambda here is just a constant scaling factor. So applying that to the numerator on the left-hand side, right, we get an upper bound on the array gain given by this equation, which is just begging us, right, to cancel out the W's. Right, and so our array gain, for the case when is less than the norm of Vt squared, so the norm of the replica vector of the look direction, again, where to get to this formula, we did assume that the noise in our sensors was uncorrelated, right? That we had a scaled identity matrix for the noise covariance. We'll talk in a few weeks. And for the way we've defined replica vectors in this class, where each element of this, right, is just an exponential, the norm of any replica vector is going to be n. Right, so this tells me that the array gain is less than or equal to the number of sensors, which again makes sense because if I'm averaging n things, which is kind of what a beamformer does for unity gain, if I'm averaging n things, the most I can reduce the uncorrelated noise by is n. Right, so I've already done that, and it's only equal if the weight vector is a scaled version of VT, right? If these two vectors are scaled versions, right? So for unity gain, W equal 1 over n times VT is the unique solution, if and only if, right, is the unique solution for unity gain that maximizes the white noise gain for a beamformer. And so this is, again, a very quick proof. It doesn't involve gradients and all this worrying about complex gradients. The nice thing about Cauchy Schwartz proofs is they're very elegant when you find them. When it gets more complicated, even I don't always see them right away. Sometimes I find them after I prove it the long way. But this is a helpful tool to have in your toolbox, so that's why I wanted to add this sort of little bonus trailer at the end of this episode to go over a Cauchy Schwartz type proof for array gain. Okay, so again, I'll stop here. This is a very long video, but it's an important idea of finding the beamformer to maximize the array gain and white noise, and that the answer, again, I've shown you several different ways of thinking about it and interpreting it, is the conventional beamformer. All right, that's all for now. See you next time.